Look up at the night sky, and you'll see a tapestry of stars, familiar constellations, the occasional planet, maybe even a distant galaxy, if you're lucky. But what if I told you that just beyond what your eyes can see, in our cosmic neighborhood known as the Local Group, there are objects so bizarre they challenge everything we think we know about the universe? We're talking about structures and phenomena that defy logic, spark heated debates among scientists, and leave even the most seasoned astronomers scratching their heads. From rogue black holes wandering between galaxies to mysterious, starless clouds of pure gas that glow with no apparent source of energy, the Local Group is packed with enigmas waiting to be unraveled. This isn't just a story about distant, indifferent space. It's a reminder that our corner of the cosmos is far stranger and more dynamic than we often assume. The Local Group, home to our Milky Way and over 50 other galaxies, isn't some static backdrop. It's a living, evolving network where the rules of physics sometimes twist into something unexpected. Some of these objects seem to exist against all odds, like cosmic glitches in the system. Others hint at forces we haven't yet discovered, lurking in the shadows of our understanding. And the wildest part, many of them are hiding in plain sight, closer than you'd think. Over the next few minutes, we're diving into 30 of the most peculiar objects in the Local Group, each one a puzzle piece in the grand mystery of our universe. Some will make you question reality, others might just rewrite the textbooks, whether it's a galaxy with no dark matter, a star cluster moving too fast to exist, or a cosmic collision that shouldn't have happened. These aren't just curiosities, they're clues. Clues that could help us unlock the secrets of gravity, dark energy, and maybe even the origins of everything. So buckle up. By the time we're done, you'll never look at the night sky the same way again. The Andromeda galaxy, our closest galactic neighbor, holds a secret at its heart, one that has puzzled astronomers for decades. Instead of a single, well-defined core like most galaxies, Andromeda boasts two distinct nuclei, a feature so unusual it defies conventional theories of galactic evolution. This double nucleus isn't just a visual oddity, it's a cosmic riddle wrapped in layers of gravitational chaos. The primary nucleus is a dense, star-packed region typical of spiral galaxies, but the second, offset by a mere 5 light-years, is fainter, cooler, and seemingly out of place. So how did this anomaly come to be? One leading theory suggests a violent galactic merger in Andromeda's distant past. Imagine two smaller galaxies colliding, their cores dancing around each other in a gravitational tug of war until one was torn apart, leaving behind a debris trail and this enigmatic secondary nucleus. Another possibility involves the supermassive black hole at Andromeda's center. Could it be surrounded by a lopsided disk of stars, creating the illusion of a second core? Hubble's razor-sharp observations have only deepened the intrigue, revealing intricate star motions that hint at forces we don't yet fully understand. What makes this doubly fascinating is the challenge it poses to our models of galaxy formation. If mergers or black hole dynamics can warp a galaxy's heart so dramatically, what else might we be missing? The answer could rewrite how we see not just Andromeda, but every galaxy in the cosmos. And here's the kicker, because Andromeda is on a collision course with our Milky Way. Studying its strange core might give us a preview of the chaos awaiting our own galaxy in billions of years. Talk about a cosmic cliffhanger. The Triangulum galaxy, or Messier 33, should be just another ordinary spiral galaxy, beautiful, yes, but predictable in the grand scheme of things. Yet this cosmic pinwheel, the third largest member of our Local Group, harbors a secret that's turned astrophysics on its head. It's missing most of its dark matter. That's right, the invisible scaffolding thought to hold galaxies together. Triangulum seems to have misplaced it. Dark matter isn't just a minor component of galaxies, it's the glue. Typically, galaxies like our Milky Way contain about 5 times more dark matter than visible stars and gas, but Triangulum, studies of its rotation curve, the way stars and gas move within it reveal a shocking deficit. There's barely enough dark matter here to explain its structure, as if someone forgot to pack the universe's most essential ingredient. So where did it go? One possibility is tidal stripping. Over billions of years, Triangulum's close encounters with Andromeda, its massive neighbor, might have violently ripped away its dark matter halo, leaving behind a galaxy running on fumes. Imagine two dancers twirling too close, the stronger partner yanking away the other's costume. But there's a problem. Triangulum stars show no signs of the kind of damage you'd expect from such a brutal gravitational assault. Then there's the measurement camp. Could we just be wrong? Some scientists argue that Triangulum's unusual orientation, tilted nearly edge onto us, makes its motion harder to track, leading to faulty dark matter estimates. Others propose that the galaxy's dark matter isn't missing at all. It's just spread out in a diffuse, nearly invisible halo that current tools can't detect. But the most tantalizing theory, maybe Triangulum never had much dark matter to begin with. If true, this would upend our understanding of how all galaxies form. We've long assumed dark matter is the seed around which visible galaxies grow. But what if some galaxies find another way? Triangulum's defiance could hint at an entirely unknown path to galactic existence, one that doesn't play by the rules we thought were universal. For now, this cosmic rebel remains an open case, challenging astronomers to rethink the foundations of galactic evolution. Whether it's a victim of cosmic theft, a case of mistaken identity, or a rule-breaking outlier, Triangulum proves one thing: even in our own backyard, the universe still has surprises up its sleeve. Most galaxy clusters are cosmic graveyards, vast, ancient cities where star formation has long since fizzled out, leaving behind aging red giants and the faint glow of dying embers. But buried in the Local Group, there's a raging inferno of stellar birth that shatters every expectation: the Phoenix Cluster. This monstrous structure isn't just alive, it's setting records, churning out new stars at a rate 700 times faster than our Milky Way. What makes this even more astonishing is that it shouldn't be possible. At the heart of the Phoenix Cluster lies a supermassive black hole, and according to our current understanding, these behemoths should suppress star formation, not ignite it. So what's going on? The answer lies in something called a cooling flow. Normally, when gas in a galaxy cluster gets too hot, heated by the black hole's violent outbursts, it can't cool down enough to collapse into new stars. But the Phoenix Cluster is different. Chandra X-ray observatory data reveals rivers of gas cooling at staggering speeds, plummeting from millions of degrees to near absolute zero in cosmic terms. This chilled gas then cascades into the cluster's core, fueling a non-stop stellar baby boom. Here's where it gets even weirder. The supermassive black hole at the center isn't just sitting idle, it's caught in a bizarre balancing act. Instead of blasting away nearby gas with its energy, as black holes typically do, it's actually permitting this gas to cool, creating a cosmic conveyor belt of star-forming material. It's like a dragon sitting atop a hoard of gold, but instead of guarding it jealously, it's tossing coins to the crowd below. The implications are staggering. If the Phoenix Cluster can defy the red and dead fate of its peers, it forces us to reconsider how galaxies evolve. Could there be other clusters out there, hidden in plain sight, where black holes and star formation exist in this strange harmony? Or is the Phoenix Cluster a rare cosmic fluke, a temporary fireworks display in an otherwise quiet universe? One thing's certain: this celestial overachiever is rewriting the rules, proving that even in the oldest, most massive structures, the universe still has surprises up its sleeve. And with every new star it births, the Phoenix Cluster isn't just lighting up the cosmos, it's illuminating the gaps in our understanding of how galaxies live, die, and sometimes, against all odds, rise from the ashes. Tucked away in the local group, two cosmic oddballs are rewriting the playbook on how galaxies move and how they're built. First up, Leo the First, a dwarf galaxy with an attitude problem. While most satellite galaxies orbit their hosts like orderly clockwork, Leo the First does the exact opposite. It's spinning backward around the Milky Way, a celestial rebel defying galactic etiquette. This isn't just a quirky detail, it's a clue to one of astronomy's biggest unsolved mysteries: how galaxies assemble their entourages. The prevailing theory says small galaxies like Leo the First should fall into orbit around larger ones, moving in the same direction as their host's rotation. But Leo's counter-rotation throws a wrench in that idea. Did it get flung into this backward path by a long-ago collision? Could it be an interloper captured from some other corner of the cosmos? Or does its strange orbit hint at something even stranger, like invisible currents of dark matter tugging it off course? Every possible explanation forces us to rethink how gravity sculpts galactic neighborhoods. Meanwhile, over in the constellation Sagittarius, another rule breaker raises entirely different questions. NGC 6822, nicknamed Barnard's Galaxy, is like a living fossil, a time capsule from the universe's childhood. Most galaxies, including our own, are filled with stars enriched by generations of supernova, packed with heavy elements like iron and gold. But Barnard's Galaxy hosts stars so primitive they're practically metal-free, shimmering relics from an era before cosmic pollution. These stars shouldn't exist in a galaxy this close to us. They're the astronomical equivalent of finding a medieval village untouched by modern technology. How did Barnard's Galaxy avoid the chemical evolution that transformed every other galaxy around it? One possibility: it's been left alone, drifting in isolation for billions of years, never merging with larger galaxies that would have seeded it with heavier elements. Another theory suggests it's a late bloomer, forming stars so slowly that it never built up the metallicity of its peers. Together, these two misfits, Leo the First with its backward stroll and Barnard's Galaxy with its ancient stars, paint a messy picture of galactic evolution. They remind us that the local group isn't just a collection of predictable spirals and dwarfs. It's a menagerie of exceptions, each with its own story to tell. And buried in those stories might be the keys to understanding how all galaxies, from the tiniest dwarfs to the grandest spirals, came to be. The universe, it seems, still has a few tricks up its sleeve. Stretching across the night sky like ghostly ribbons of starlight, the Sagittarius dwarf's tidal streams tell a story of cosmic destruction and a preview of our own galaxy's fate. This once proud dwarf galaxy didn't just collide with the Milky Way, it was unraveled by it, stretched into sprawling tendrils of stars and gas that now encircle us like a celestial spiderweb. These streams, discovered in the 1990s, aren't just debris, they're a fossil record of gravity's relentless power, and a roadmap to understanding how galaxies grow by devouring their neighbors. What makes these streams so extraordinary is their sheer scale. They wrap around the Milky Way not once, but multiple times, forming a complex, nested structure that traces the Sagittarius dwarf's final orbits over billions of years. Imagine flinging a handful of spaghetti against a wall the way the strands splay out in arcs. That's essentially what happened here, except on a galactic scale. Stars torn from the dwarf galaxy were flung into elongated orbits, creating luminous trails that crisscross the entire sky. But here's where it gets even wilder. These streams aren't just relics of the past, they're alive with motion. Studies of their stellar motions reveal the Milky Way isn't the smooth, symmetrical disk we often picture. The streams wiggle and warp in ways that betray hidden lumps and bumps in our galaxy's dark matter halo, like sonar pinging off the hull of an invisible ship. Some sections of the streams are even kinked, suggesting the Milky Way's gravitational field was jostled by another passing galaxy long ago, a cosmic encounter we'd have never known about without these stellar breadcrumbs. And then there's the future they hint at. Right now, the Milky Way is digesting the Sagittarius dwarf like a snake slowly dissolving a meal. But in about 4 billion years, we'll be the ones getting swallowed by the Andromeda galaxy. The same tidal forces that shredded the Sagittarius dwarf will tear spiral arms from the Milky Way, flinging stars into chaotic new orbits. The difference? This time, we'll be inside the collision, watching our galaxy's structure rewrite itself in real time. The Sagittarius streams are more than just a casualty report, they're a masterclass in galactic archaeology. By reading their twists and turns, astronomers are piecing together a biography of the Milky Way, one that includes past mergers we never witnessed and future transformations we can't yet imagine. They remind us that even the grandest galaxies aren't immutable castles in the sky, they're living, changing things, built one cannibalized dwarf at a time. Among the countless galaxies in the local group, none stop astronomers in their tracks quite like Hoag's object. This cosmic bullseye floating serenely in the constellation Serpens looks less like a galaxy and more like a piece of abstract art, a shimmering golden ring encircling a radiant red core with nothing but darkness separating the two. It's so geometrically perfect that when it was first discovered in 1950, astronomers suspected an imaging glitch. But Hoag's object is very real, and its existence challenges our understanding of how galaxies assemble themselves. The mystery lies in that pristine ring. Most ring galaxies, like the famous cartwheel, are messy splatter patterns, the aftermath of a smaller galaxy plowing through a larger one, sending shockwaves of star formation rippling outward. Hoag's object shows no such chaos. There's no visible debris, no sign of a recent collision, and no neighboring galaxy that could have triggered this structure. The ring floats around the core like smoke from a magician's trick, defying conventional explanations. One theory suggests a slow-motion upheaval. Over billions of years, gravitational instabilities in the galaxy's disk could have caused stars and gas to migrate outward, piling up into that impossibly symmetrical ring. It's like spinning a drop of ink in water. Centrifugal forces stretch it into a perfect circle. Supporting this idea are faint, ancient stars detected between the core and the ring, hinting at a bridge of material that's since faded. Then there's the collision camp. Some argue Hoag's object did suffer a head-on impact, but so long ago that all traces of the intruder have vanished. Simulations show that under just the right conditions, a small galaxy striking a larger one dead center, the resulting ring, can settle into eerie symmetry over time. The catch: no known collision produces a ring this clean, leaving theorists scrambling for adjustments. But the most mind-bending detail: Hoag's object isn't alone. Peering into the darkness behind it, astronomers spotted another ring galaxy, perfectly aligned in the same plane. This cosmic coincidence, two pristine rings stacked like dinner plates, raises an even wilder possibility: that Hoag's object represents an entirely new class of galaxy, one that forms through mechanisms we haven't even imagined yet. Whether it's a relic of forgotten violence or a self-assembling masterpiece, Hoag's object proves that even the simplest shapes in space can hide the deepest secrets. And in its perfect symmetry, we're reminded that the universe often saves its most dazzling puzzles for the patient observer. Float through the southern skies and you'll spot two hazy patches of light, the large and small Magellanic Clouds, our galaxy's most famous dwarf companions. But look closer, and their true drama unfolds between them, where a river of gas stretches across the cosmos like a celestial bridge. This is the Magellanic Stream, a filament of hydrogen so vast it would take light 600,000 years to traverse its length. And here's the twist: this isn't just stray gas. It's the shredded remains of a cosmic tug-of-war, a battlefield where gravity, time, and galactic collisions have left their mark. The story begins billions of years ago, when the Magellanic Clouds, now dancing around the Milky Way, were still independent galaxies drifting through the void. As they drew closer to each other, their mutual gravity began to pull them apart, stripping away their gas in long, wispy tendrils. Then came the Milky Way's turn. Our galaxy's immense gravity didn't just distort the clouds, it flayed them, yanking their gas into this sprawling ribbon that now arcs across nearly half the visible sky. What makes the Magellanic Stream so fascinating isn't just its size, but its future. Locked within those gas clouds are the seeds of new stars, or at least they should be. Normally, when gas is compressed by gravity, it collapses into glowing stellar nurseries, yet the stream remains eerily dark, a river without stars. Why? The answer might lie in its turbulent past. Simulations suggest the gas was stretched so thin during its violent ejection that it simply couldn't clump together. Or perhaps the Milky Way's halo of hot plasma is ionizing the gas, preventing it from cooling enough to ignite new suns. But there's a ticking clock here. As the Magellanic Clouds continue their orbits, they're dragging the stream closer to the Milky Way's disk. In a few 100 million years, this river of gas will begin raining down onto our galaxy, fueling a fresh wave of star formation. It's a delayed cosmic feast, one that might birth millions of new stars, lighting up the night skies of any future civilizations. The stream also holds clues to a deeper mystery. By studying its twists and kinks, astronomers have found evidence that the Milky Way might be heftier than we thought. Its dark matter halo exerting far stronger gravitational pull than expected. Others argue the stream's structure hints at an unseen interloper, a rogue galaxy or dark matter subhalo that once barreled through the clouds, adding chaos to an already violent process. In the end, the Magellanic Stream is more than just a scar of galactic interactions. It's a living timeline, documenting the ebb and flow of gravity's influence over billions of years. And as it drifts ever closer to the Milky Way, it serves as a reminder. Even the quietest corners of our local group are chapters in an epic, ever-unfolding story. M32 might look like just another speck next to Andromeda's sprawling grandeur, but this tiny satellite galaxy is hiding a monstrous secret, one that defies all expectations. For its size, M32 is absurdly dense, cramming billions of stars into a space barely 1% the Milky Way's volume. And at its heart, a supermassive black hole so disproportionately massive it rivals the one at the center of our own galaxy. How does a cosmic afterthought like M32 end up with such a heavyweight anchor? The answer might rewrite the story of how galaxies evolve and what happens when they're torn apart. The numbers alone are staggering. M32's black hole weighs in at around 3 million solar masses, comparable to Sagittarius, a star in the Milky Way. But here's the catch: our galaxy spans 100,000 light-years. M32 stretches just 6,000. It's like finding a skyscraper squeezed into a shoebox. This bizarre mismatch has led astronomers to a radical theory. M32 isn't a normal dwarf galaxy at all. It might be the mangled corpse of something far larger, a galaxy stripped down to its bare bones. Imagine a spiral galaxy, once as majestic as Andromeda, venturing too close to its colossal neighbor. Over billions of years, Andromeda's gravity peels away its outer stars, leaving only the densest core intact, a process called tidal stripping. The stars near the center, including those orbiting the black hole, cling on desperately, while the rest are scattered into the cosmic void. What remains is M32, a galactic survivor compacted by violence into a dense nugget of starlight and shadow. Supporting this idea are M32's unusually bright core and its population of ancient stars, both hallmarks of a galaxy that's endured a traumatic past. Then there's the black hole's position, perfectly centered, as if it's the last jewel in a plundered crown. If M32 was once larger, its black hole wouldn't have grown to this size in isolation. It would have been fed by the larger galaxy's ample gas reserves long before the catastrophe. But not everyone's convinced. Some argue M32 could have formed this way naturally, its black hole growing through some rare, hyper-efficient feeding process we don't yet understand. Others point to the lack of obvious debris around Andromeda. Where are the stars that should have been ripped away during this theoretical collision? The implications stretch far beyond M32. If stripping can produce galaxies this dense, entire categories of ultra-compact dwarfs might actually be the remnants of larger galaxies, their origins erased by time and gravity. And if black holes can persist, even thrive, in these shattered cores, it raises a chilling question. How many other cosmic ghosts are lurking in the local group, masquerading as ordinary dwarfs while hiding violent past? M32 might be small, but its secrets loom large, forcing us to rethink what happens when galaxies collide, and what survives the wreckage. IC10 might be one of the smallest galaxies in the local group, but don't let its size fool you. This cosmic runt is punching way above its weight class. While most dwarf galaxies fade into obscurity, IC10 is a raging powerhouse, cranking out new stars at a rate that puts giants like the Milky Way to shame. But here's the real kicker. Lurking in its chaotic starburst heart is an army of black holes, far more than any galaxy this size should logically contain. Not just any black holes, either stellar mass black holes locked in deadly dances with companion stars, their violent orbits spraying gamma rays across the cosmos like celestial fireworks. So how does a galaxy no bigger than a tenth of the Milky Way end up with such a monstrous surplus? The answer lies in its breakneck star formation. IC10 is what astronomers call a starburst galaxy, a place where gas clouds collapse into stars at a frenzied, almost reckless pace. Picture a fireworks factory operating at 10 times capacity, with explosions lighting up the sky every few seconds. In environments this extreme, massive stars burn bright and die young, collapsing into black holes after just a few million years. Normally, these black holes would drift apart, but IC10's dense core keeps them packed together like marbles in a jar, increasing the odds of pairing up with surviving stars. But the plot thickens. Many of these black holes aren't just orbiting stars, they're devouring them, creating what's known as X-ray binaries. As gas from the companion star spirals into the black hole, it heats up to millions of degrees, blasting out high-energy X-rays. NASA Chandra X-ray Observatory has spotted dozens of these systems in IC10, a number that defies statistical probability for a galaxy its size. Some of these binaries are so bright they outshine entire galaxies in X-ray light. And then there's the gamma-ray connection. IC10 sits suspiciously close to one of the most persistent mysteries in modern astronomy, a faint but baffling excess of gamma rays permeating the local group. While the source of this radiation is still debated, IC10's black hole binaries are prime suspects. Every time one of these monsters tears into its stellar companion, it doesn't just emit X-rays. It can unleash jets of particles moving at nearly the speed of light, colliding with interstellar gas to produce gamma rays. Could this tiny galaxy be secretly fueling a large-scale cosmic phenomenon? The implications are staggering. If IC10's black hole population is indeed behind the local group's gamma-ray haze, it suggests that small, overlooked galaxies might play an outsized role in shaping the high-energy universe. It also raises a tantalizing question. Are there other starburst dwarfs hiding in plain sight, their black hole armies quietly influencing the cosmos in ways we're only beginning to grasp? IC10 may be small, but it's forcing us to think big, proving once again that the universe's strangest stories often come in the most unassuming packages. In the local group's cosmic menagerie, no two galaxies could be more different than Sexton's A and the Pegasus dwarf. They're like celestial twins separated at birth, one bathed in the raw glow of newborn stars, the other shrouded in near-total darkness. Sexton's A is a time capsule, a bubble of primordial gas so untouched by cosmic pollution it's as if the universe forgot to age it. Meanwhile, the Pegasus dwarf is a ghostly paradox, a flicker of starlight drowned in an ocean of invisible mass. Together, they're a masterclass in how galaxies can defy expectations. Let's start with sextans A. Most galaxies are littered with dust-charred remnants of dead stars that seed new generations. But this small, irregular galaxy is almost sterile, its gas so pristine it's like peering into the universe's toddler years. Without dust to block starlight, Sextans A's young blue stars blaze with unnatural clarity, their ultraviolet radiation tearing through space unimpeded. This isn't just a cosmetic quirk. That lack of dust means Sextans A's star formation operates differently. Normally, dust grains act as cosmic refrigerants, helping gas clouds cool and collapse. Here, the process is raw and inefficient, like trying to build a snowman in a desert. Yet somehow, against the odds, Sextans A keeps birthing stars, just in fits and starts, as if the galaxy itself is figuring out the rules as it goes. Then there's the Pegasus dwarf. If Sextans A is all flash and fire, Pegasus is almost all shadow. This dim, sparsely populated galaxy is 99% dark matter, a ratio so extreme it makes even other dwarfs look overstuffed with stars. At first glance, that seems impossible. How can something so faint be so heavy? The answer lies in its feeble starlight. Pegasus's visible stars are like a handful of fireflies in a football stadium, barely hinting at the invisible structure holding them up. Its dark matter halo must be colossal, a gravitational anchor so dense it warps the very fabric of space around it. What makes Pegasus truly bizarre is how it survived. Galaxies this small and diffuse should have been torn apart by now, shredded by encounters with giants like Andromeda. Instead, Pegasus endures, its dark matter acting like an unshakable skeleton. Some theorists argue it's a failed galaxy, one that never gathered enough gas to form stars in the first place. Others suggest it's the survivor of a catastrophic collision, its stars scattered while its dark halo remained intact. Either way, Pegasus forces us to confront an uncomfortable truth. Dark matter isn't just a passive ingredient, it can dominate a galaxy's fate, the juiciest irony. These two opposites might actually be related. Some simulations suggest galaxies like Sextans A, low in metals, rich in gas, could evolve into Pegasus like ghosts over billions of years. As their gas gets blown away by stellar winds or stolen by larger neighbors, only the dark matter remains, a silent witness to their former glory. If true, we might be looking at two chapters of the same story, one galaxy at the beginning, the other at the end. Sextans A and the Pegasus dwarf are more than curiosities, they are boundary pushers. One shows how galaxies thrive without the usual tools. The other proves how much of their existence hinges on forces we can't even see. Together, they remind us that the local group isn't just a collection of similar spirals and dwarfs, it's a laboratory of extremes, where every outlier holds a clue to the universe's grander workings. Hovering on the outskirts of Andromeda like a celestial jewel, Major Roman II isn't your average globular cluster. Most of these ancient stellar swarms are simple relics, homogeneous balls of stars born together in the early universe. But Major Roman II breaks the mold twice over. It's 10 times more massive than typical globulars, and its stars aren't all the same age or composition. This cosmic oddball has astronomers debating whether it's a cluster at all, or the stripped-down heart of a devoured dwarf galaxy. The clues start with its stars. While normal globulars contain stars forged in a single burst, Major Roman II population spans a staggering range of metallicities, the astronomical term for heavy elements. Some stars are metal-poor, pristine relics from the universe's first billion years. Others are rich in metals, suggesting they formed later from gas enriched by generations of supernova. This spread implies multiple epochs of star formation, something globulars simply don't do. It's like finding a retirement home where some residents are centenarians born in the 1800s, while others are millennials with smartphones. Then there's the black hole question. Hubble observations reveal stars near Major Roman II core whirling at breakneck speeds, hinting at an invisible gravitational anchor. likely an intermediate mass black hole 20,000 times heavier than our Sun. Such black holes are vanishingly rare in globular clusters, but they're textbook features of dwarf galaxies. Combine this with Magellanic Clouds complex structure. Its stars aren't smoothly distributed but clumped in subgroups, and the evidence starts piling up. But the plot thickens. If Magellanic Clouds is a devoured dwarf's core, whereas the rest of it, computer simulations suggest Andromeda's tides could have stripped away the original galaxy's outer stars over billions of years, leaving only this dense nugget behind. Supporting this, Magellanic Clouds orbits Andromeda at an unusual angle, just like other suspected galactic remnants. Yet skeptics point out that some of its stars orbit backwards relative to the cluster's motion, a twist that doesn't neatly fit the dwarf galaxy theory. The implications stretch far beyond Magellanic Clouds. If it's a galactic survivor, it means Andromeda's halo could be littered with similar corpses, their origins erased by time. It also challenges how we define globular clusters altogether. Are they always born as simple stellar collectives, or do some form through violence, their complexity a scar of past mergers? Magellanic Clouds refuses to give easy answers, standing as a tantalizing bridge between two cosmic classifications, and a reminder that even familiar objects can hide revolutionary secrets. NGC 185 should be just another quiet dwarf galaxy, small, faint, and unremarkable. But lurking in its shadows is a mystery that crackles with high-energy intrigue. This unassuming satellite of Andromeda is pumping out gamma rays, the most energetic light in the universe, with no obvious source, no active black hole. No rampant star formation, just a faint, ancient stellar population and this eerie, unexplained glow. So what's powering NGC 185 ghostly emissions? The answer might rewrite our understanding of dark matter, or reveal a hidden population of cosmic lighthouses. Gamma rays don't just appear out of nowhere. They're the universe's fireworks produced by the most violent events, supernova colliding neutron stars or matter spiraling into black holes. Yet NGC 185 lacks all the usual suspects. Its stars are old and sedate, with no recent supernova to spark such energetic outbursts. That leaves two tantalizing possibilities, each more mind-bending than the last. First, the dark matter angle. Many theories suggest dark matter particles, when they collide, could annihilate each other in bursts of gamma radiation. If true, NGC 185 dense dark matter halo, common in dwarf galaxies, might be a natural laboratory for this process. The catch: these signals should be faint and uniform, not patchy like the gamma rays we're actually detecting. Then there's the pulsar scenario. These rapidly spinning neutron stars beam out radiation like cosmic searchlights. Normally, they're found in star-forming regions, but NGC 185 aging stellar population could host a secret coda of millisecond pulsars, ancient relics spun up by stolen stellar material. These vampiric pulsars would be nearly invisible in optical light, but could collectively produce NGC 185 gamma-ray haze. Supporting this, Fermi telescope data shows the gamma rays clumped near the galaxy's core, right where old stars congregate. But here's the twist: even if pulsars are the culprit, their sheer number in NGC 185 defies expectations. This tiny galaxy would need hundreds of them to explain the signal, far more than any dwarf of its size should logically contain. Unless, of course, pulsars form more efficiently in environments we don't yet understand. The stakes are high. If dark matter's behind this, NGC 185 could be our best shot at detecting its elusive particles. If it's pulsars, we're staring at a new chapter in stellar evolution. Either way, this quiet dwarf is shouting something extraordinary. We just have to decipher what it's trying to say. The Hercules dwarf should be a simple, round blob of stars like most of its cosmic cousins. but instead it's stretched into a cosmic taffy, a lopsided, elongated smear of starlight that defies the typical dwarf galaxy blueprint. This odd shape isn't just a curiosity, it's a snapshot of gravity's relentless grip and a clue to one of astronomy's most stubborn puzzles, the missing satellites problem. First, the physics of the stretch. Hercules' stars aren't randomly scattered, they form a distinct cigar-shaped stream, with one end noticeably denser than the other. The leading theory, the Milky Way's tidal forces are literally pulling the galaxy apart. Imagine swinging a water balloon in circles until it deforms into a teardrop. That's essentially what's happening here, but on a galactic scale. Over billions of years, our galaxy's gravity has yanked stars from Hercules' outer edges, flinging them into elongated orbits while the core clings together. What we're seeing is a galaxy in the midst of being unraveled, its stars slowly joining the Milky Way's halo like cosmic tributaries, but here's where it gets thorny. Hercules' tortured shape might explain why so many dwarf galaxies aren't where we expect them. According to dark matter simulations, the Milky Way should be surrounded by hundreds of small satellite galaxies, yet we've only found a few dozen. The discrepancy, dubbed the missing satellites problem, has haunted astronomers for decades. Hercules offers a compelling solution. Many of these dwarfs might already be in the process of dissolving, stretched so thin by tidal forces that they're practically invisible. Their stars still exist, they're just smeared across vast, faint streams that blend into the galactic background. Supporting this idea, Hercules isn't alone. Several other dwarfs, like Ursa Minor and Draco, show similar distortions, hinting at a broader pattern of tidal disruption. Even more telling, some of these streams discovered in recent years, like the Phoenix stream, don't have obvious progenitor galaxies. Could these be the final threads of dwarfs that Hercules-like stretching erased entirely? Yet not everyone's convinced. Some argue Hercules' elongation might be intrinsic, a relic of its chaotic formation rather than external forces. Others point out that if tidal shredding were this efficient, we'd see more intermediate stage dwarfs like Hercules, not just the obvious victims and ghosts. The debate boils down to a cosmic census problem. Are we bad at counting dwarfs, or did the models overpredict their numbers? Regardless of the answer, Hercules forces us to confront the fragility of small galaxies in a giant shadow. It's a reminder that the local group isn't a static snapshot. It's a dynamic battlefield where gravity sculpts, distorts, and sometimes erases entire galaxies over time. And if Hercules is indeed a canary in the coal mine, its stretched-out stars might be the key to finding countless other, missing dwarfs hiding in plain sight. The real kicker, this process isn't just ancient history, it's happening right now. Every orbit Hercules completes around the Milky Way strips away a few more stars, inching it closer to oblivion. One day, far in the future, Hercules will cease to exist as a distinct galaxy, its stars absorbed into the Milky Way's halo. Until then, it's a living lesson in cosmic destruction and a tantalizing hint at what else might be lurking or unraveling just beyond our view. Stretching across the cosmos like a phantom limb, a tendril of hydrogen gas trails behind the Triangulum galaxy, a filament so vast it could wrap around the Milky Way 3 times. This isn't just another wisp of interstellar material. It's a cosmic fossil, a 300,000 light-year-long mystery that whispers of ancient collisions, intergalactic theft, or perhaps something even stranger. What makes this filament so baffling isn't just its size, but its defiance of expectations. Gas streams like this should dissipate over time, torn apart by galactic tides or evaporated by ultraviolet radiation. Yet here it remains, stubbornly intact, as if the universe hit pause on its destruction. Theories about its origins split into 2 camps. The first points to a violent past. Around 2 billion years ago, Triangulum might have had a close encounter with Andromeda, our local group's titan, whose gravity could have ripped gas from Triangulum's disk like taffy, stretching it into this impossibly long ribbon. Simulations show such interactions can produce tidal tails, but none match the sheer scale of this filament, unless, of course, the collision was more catastrophic than we've imagined, leaving behind not just a gas stream but an entire galactic scar. Then there's the intergalactic accretion theory. Space between galaxies isn't entirely empty. It's threaded with faint rivers of primordial hydrogen, leftovers from the universe's birth. Some suggest Triangulum is sailing through one of these cosmic currents, scooping up gas like a ship plowing through fog. But there's a hitch. The filament structure is too coherent, too organized for random accretion. Its smooth, tapered shape suggests directional flow, as if guided by invisible hands. Could dark matter be funneling this gas into place, or is some other force at work? The plot thickens when we examine the filament's chemistry. Unlike the metal-rich gas inside galaxies, this stream is pristine, almost entirely hydrogen and helium, untouched by the polluting breath of stars. That purity suggests it's either very old, predating Triangulum itself, or was ripped from the galaxy's outermost edges where heavier elements are scarce. Either scenario forces us to reconsider how galaxies gather and lose their gas, the lifeblood of star formation. But the real shocker, this filament might not be alone. Recent radio telescopes have detected faint hydrogen tendrils around other local group galaxies, hinting at a hidden web of gas connections weaving our cosmic neighborhood together. If confirmed, these filaments could rewrite the story of galactic evolution, revealing a universe where galaxies aren't isolated islands but nodes in a vast, flowing network. Triangulum's gargantuan tendril might just be the first thread we've pulled in a much larger tapestry, one that could unravel how galaxies breathe, feed, and grow across eternity. The Milky Way isn't the only galaxy with a strange entourage of dwarf satellites. Andromeda has its own cosmic conundrum, and it's rewriting the rules of galactic companionship. Most cosmological models predict that satellite galaxies should swarm their hosts like bees around a hive, scattered in a messy, three-dimensional cloud. But when astronomers mapped Andromeda's dwarfs, they found something eerie. Nearly 30 of them are aligned in a single, razor-thin plane, rotating in sync like a giant celestial carousel. This isn't just a statistical fluke, it's a direct challenge to our understanding of how galaxies form. The odds of this happening randomly, astronomers put it at 1 in 10,000. Imagine tossing a handful of confetti into the air only to watch every piece land perfectly in a straight line. That's the level of improbability we're dealing with. What makes this satellite plane even stranger is its eerie resemblance to a similar structure around the Milky Way. Both galaxies, despite being separated by 2.5 million light-years, host dwarf galaxies that orbit in these bizarrely aligned disks. Coincidence unlikely. The universe rarely repeats patterns without a reason. So what's causing this cosmic synchrony? One controversial theory suggests these satellites aren't independent galaxies at all. They might be fragments of a single, ancient dwarf galaxy torn apart by Andromeda's gravity billions of years ago. Picture a snowball flung against a wall, shattering into dozens of icy chunks that continue moving in the same direction. If true, this would explain the shared orbit, but there's a catch. Many of these dwarfs show wildly different ages and chemical compositions, as if they came from completely different origins. Then there's the dark matter angle. Current simulations assume dark matter halos are roughly spherical, with satellites scattered randomly within them. But if dark matter itself flows in vast, invisible rivers, cosmic highways sculpted by the early universe's web-like structure, it could funnel dwarf galaxies into these aligned planes. Some theorists even propose that dark matter might have unexpected properties, like long-range interactions that lock satellites into synchronized orbits over time. But the most radical idea, these planes might be evidence of modified gravity. The standard model of cosmology, known as lambda CDM, struggles to explain these structures. Could gravity itself behave differently on galactic scales, sculpting satellites into disks without the need for dark matter at all? It's a long shot, but when the universe throws you this many curveballs, sometimes you need to rethink the rules of the game. Whatever the answer, Andromeda's satellite plane isn't just a curiosity, it's a crack in the foundation of modern cosmology. If dwarf galaxies aren't distributed randomly, it means our simulations of galaxy formation are missing something fundamental, something that's been hiding in plain sight right next door. And as we peer deeper into the local group, one thing becomes clear: the universe loves to arrange its mysteries in perfectly straight lines. Most galaxies in the local group bear the scars of cosmic collisions, tidal tails, distorted shapes, and mixed-up stars telling tales of violent encounters. But drifting alone through the void, nearly 3 million light-years from the Milky Way, the Wolf-Lundmark galaxy has escaped it all. This tiny, ragged smudge of stars is one of the most isolated galaxies known, a cosmic hermit that spent nearly 13 billion years evolving in near-total solitude. While its neighbors were torn apart and rebuilt by gravitational encounters, WLM remained untouched, a pristine time capsule of the early universe's conditions. What makes WLM so extraordinary isn't just its loneliness, but what that solitude has preserved. Unlike galaxies like Andromeda or the Milky Way, which have cannibalized smaller neighbors to grow, WLM stars are almost entirely homegrown. Its chemical makeup reads like a ledger of unaided evolution, gas unpolluted by mergers, stars born from raw, primordial material. Even its structure, loose, irregular, and chaotic, reflects a galaxy that's never felt the shaping hand of external forces. It's as if someone pressed pause on galactic evolution shortly after the Big Bang and forgot to restart it. But isolation comes at a cost. Without fresh gas from cosmic collisions, WLM struggles to form new stars. Its sparse interstellar medium means starbirth happens in fits and starts, leaving vast stretches of time where the galaxy flickers dimly, barely holding on. Yet somehow, against the odds, it's endured. While larger galaxies gorged themselves on mergers, WLM subsisted on meager rations, a testament to how galaxies can persist on the cosmic fringe, far from the gravitational dinner table. The most striking contrast lies in its dark matter. Unlike cluster galaxies whose halos were reshaped by endless interactions, WLM's dark matter remains undisturbed, distributed just as it was in the universe's infancy. Studying its rotation offers a rare glimpse into how dark matter behaved before large-scale structures, emerged a clue that could help unravel why some galaxies evolve into spirals while others stay forever irregular. Yet even WLM's isolation might not last. Recent measurements suggest it's drifting toward the local group's gravitational well, destined to one day join the crowded dance it's avoided for so long. When that happens, its untouched gas will ignite in a final burst of starbirth before being absorbed into larger galaxies. For now, though, WLM stands as a living relic, proof that in a universe ruled by collisions, some galaxies choose the road less traveled. Most galaxies keep their distance a frustrating secret, forcing astronomers to triangulate through layers of uncertainty. But IC 1613 isn't playing coy. It's an open book, one of the few galaxies in the local group whose position in space we know with near-perfect precision. The secret to its transparency, a celestial metronome ticking deep within its stellar heart, Lyrae stars. These ancient pulsating stars are the universe's most reliable mile markers. Unlike the more famous Cepheid variables, which can vary in brightness based on age and composition, Lyrae stars follow a strict rhythm, their pulse rates directly tied to their intrinsic luminosity. When astronomers spot one in IC 1613, they're essentially reading a cosmic odometer. Measure the star's apparent brightness, compare it to its known true brightness, and bingo! You've calculated the galaxy's distance with astonishing accuracy, down to just 3% uncertainty. That's like pinpointing the width of a soccer field from 300 miles away. This precision makes IC 1613 the gold standard for cosmic cartography. Every faint flicker of its Ara Lyrae stars helps calibrate the entire distance ladder astronomers use to map the universe. When telescopes measure farther galaxies using indirect methods, they often cross-check their results against reliable anchors like IC 1613. It's the benchmark that keeps the cosmos from slipping into a funhouse mirror of distorted scales. But the galaxy's clarity doesn't stop there. Its lack of interstellar dust, a rarity among galaxies, means starlight travels unimpeded like sunlight through crystal-clear water. This transparency allows instruments to capture its stellar population with unprecedented crispness, turning every observation into a masterclass in galactic structure. From the faintest red dwarfs to the brightest blue giants, each star stands in sharp relief against the void. What's truly remarkable is how this unassuming dwarf galaxy, barely 10,000 light-years across, has become indispensable to cosmology. While grand spirals like Andromeda steal the spotlight, IC 1613 works quietly in the background, its rhythmic stars keeping time for the entire local group. In a universe where distances are often guesswork, this galactic timekeeper remains a rare beacon of certainty, proof that sometimes the most crucial discoveries come wrapped in modest packages. Buried behind the thick dust clouds of our own Milky Way, a ghostly spiral galaxy hides in plain sight. Dwingeloo 1. This cosmic neighbor was invisible to optical telescopes for decades, its light completely swallowed by the interstellar debris of our galaxy's disk. It took the piercing gaze of radio astronomy to reveal its grand design, a sprawling pinwheel of stars and gas lurking just 10 million light-years away. The discovery was a wake-up call. If something this large could stay hidden right next door, how many other galaxies might be cloaked by the Milky Way's dusty veil? Dwingeloo 1's camouflage is almost perfect. Situated in the constellation Cassiopeia, it lies directly behind the galactic plane, the densest part of our galaxy's disk, where towering walls of cosmic dust block nearly all visible light. Even Andromeda, our brightest galactic neighbor, would fade into obscurity if placed there. But radio waves, with their longer wavelengths, slip through this murk like whispers through a closed door. When astronomers at the Dwingeloo Radio Observatory in the Netherlands scanned this region in the 1990s, they weren't just mapping hydrogen clouds. They stumbled upon an entire galaxy glowing in the silent language of atomic hydrogen emissions. The revelation was humbling. Dwingeloo 1 isn't some faint dwarf galaxy, it's a full-fledged barred spiral stretching over 30,000 light-years. Its arms ripple with star-forming regions, its core bustling with stellar activity. Under clearer skies, this would be a showpiece of the local group. Yet until radio telescopes peeled back the Milky Way's dusty curtain, we had no idea it existed. This raises an eerie possibility. Our cosmic neighborhood might be far more crowded than we think. The zone of avoidance, the region of space obscured by our galaxy's disk, covers roughly 20% of the sky. If Dwingeloo 1 is any indication, there could be dozens of hidden galaxies in this blind spot, their light smothered before reaching our telescopes. Some might even be major players, spirals or ellipticals massive enough to reshape our understanding of the local group's structure. Already, the hunt has turned up more ghosts. Dwingeloo 2, a smaller companion to its namesake, was discovered shortly after. Others, like the mysterious galaxy nicknamed Hizoa J083643, lurk even deeper in the zone, detectable only through fleeting radio whispers. Each new find chips away at the illusion that we've mapped our cosmic backyard completely. What's truly staggering is how recent this all is. Dwingeloo 1 wasn't some distant quasar at the edge of the observable universe. It was right here, hidden behind a celestial curtain we walk past every night. It forces us to confront a simple truth. Sometimes the universe's greatest secrets aren't found in the farthest reaches of space. but in the unlikeliest of places, the shadows we thought we knew. At first glance, Leo T and Andromeda Roman 19 couldn't be more different. One a spirited overachiever, the other a cosmic ghost. Leo T, a tiny dwarf galaxy no bigger than 1,000 light-years across, punches far above its weight, bursting with newborn stars despite its minuscule size. Meanwhile, Andromeda Roman 19 stretches over 20,000 light-years yet barely registers as a smudge against the blackness of space. Its light so diffuse you could stare right through it without noticing. Together, they represent two extremes of galactic existence, challenging our assumptions about how galaxies live and fade. Let's start with Leo T, the underdog that refuses to quit. Most galaxies this small are cosmic retirees, their gas reserves long since exhausted by ancient bursts of star formation or stripped away by larger neighbors. Not Leo T. Radio telescopes reveal it's brimming with hydrogen, the raw fuel for stellar birth, and its blue-tinged core glows with the unmistakable signature of young stars. This shouldn't be possible. At its size, Leo T's gravity is barely strong enough to hold onto its gas, let alone compress it into stars. Yet somehow, against all odds, it keeps churning them out like a lone baker in a deserted town still needing dough for an audience of ghosts. The secret might lie in its isolation. Nestled nearly 1.5 million light-years from the Milky Way, Leo T has avoided the gravitational harassment that sterilizes most dwarfs. Its gas remains undisturbed, pooling into dense pockets where stars ignite in sporadic bursts. But there's another twist. Leo T isn't just forming stars, it's forming them slowly. Unlike starburst galaxies that blaze through their fuel in cosmic decades, Leo T takes its time, forming maybe one star every few thousand years. It's a testament to how even the tiniest galaxies can thrive when left to their own rhythm. Then there's Andromeda Roman 19, the galaxy that forgot to be a galaxy. Despite spanning twice the diameter of the Milky Way's disk, it emits less light than some globular clusters. If you condensed all its stars into one place, they'd fit inside a sphere just a few hundred light-years wide. The rest is emptiness, a vast, shimmering haze of stars stretched so thin they barely cast shadows. What makes Andromeda Roman 19 so baffling isn't just its faintness, but its mass. Measurements of its stellar motions reveal far more gravity than its visible stars can account for, meaning this wispy giant is drowning in dark matter. In fact, its dark matter halo might be as hefty as Andromeda's own, a cosmic irony, a galaxy with the gravitational muscle of a titan dressed in the rags of a ghost. Theories about its origin range from the dramatic to the bizarre. Some suggest it's the mangled remnant of a larger galaxy, torn apart by Andromeda's tides until only its diffuse core remained. Others propose it formed this way, a dark matter-rich cloud where stars simply failed to coalesce densely, leaving a skeletal framework of stellar light. The most tantalizing idea, Andromeda Roman 19 might be a failed galaxy, a structure where dark matter clumped as usual, but gas never cooled enough to birth stars in bulk. If true, it could mean the cosmos is littered with similar phantoms, invisible to all but the most patient surveys. Together, Leo T and Andromeda Roman 19 sketch the outer boundaries of galactic possibility. One proves that even the smallest galaxies can cling to youth, while the other shows how the largest can fade into near nothingness. They force us to ask what really makes a galaxy. Is it stars, gas, or the invisible grip of dark matter? The answer might rewrite how we classify every island of light in the universe, from the brightest spirals to the faintest whispers in the dark. Winding through the constellation Pisces like a celestial serpent, the Pisces overdensity isn't just another starry patch. It's a cosmic crime scene, a sprawling trail of stellar debris that might be the last gasp of a devoured galaxy. Stretching across nearly 30 degrees of sky, 60 times the width of a full moon, This faint river of stars was first spotted in Sloan Digital Sky Survey data as an unnatural clustering of distant suns, all moving together against the backdrop of the Milky Way's halo. But here's the puzzle. Is this the shredded remains of a dwarf galaxy torn apart by our own, or something far stranger, a gravitational echo resonating through the fabric of our galaxy? The evidence leans toward carnage. Most of the Milky Way's halo is littered with similar streams, the mangled leftovers of smaller galaxies that ventured too close. But the Pisces overdensity stands out for its sheer sprawl and the bizarre motions of its stars. Unlike tidy streams like Sagittarius, which trace graceful orbital paths, Pisces stars move in chaotic, crisscrossing patterns, as if the original galaxy didn't just get shredded, it got scrambled. Spectroscopic data reveals multiple velocity groups within the stream, suggesting the victim might have been a particularly massive dwarf, its stars yanked away in successive tidal shocks over billions of years. Yet there's a competing theory that's even more mind-bending. Some astronomers argue the overdensity isn't debris at all, but a standing wave in the Milky Way's dark matter halo, a stellar ripple created by the gravitational note of our galaxy's rotation. Picture dropping a pebble into a pond. The ripples spread outward in perfect rings. Now imagine that pebble is a long-dead satellite galaxy, and the pond is the invisible sea of dark matter enveloping the Milky Way. The Pisces overdensity, in this view, is where those ripples concentrate stars like driftwood on a beach, creating the illusion of a stream without the violence. The clincher: Pisces stars are too old. If this were a recently destroyed dwarf, we'd expect some younger, metal-rich stars mixed in. Instead, its stellar population is uniformly ancient, over 10 billion years old, with hardly any heavy elements. That fits neither a typical dwarf galaxy nor the Milky Way's halo. Unless, of course, the original victim was a primordial galaxy, one of the universe's first building blocks, captured and digested so long ago its debris has fully mixed with our halo's oldest stars. What makes this cold case so urgent is its scale. If the overdensity is indeed a resonance artifact, it would be the first direct map of our dark matter halo's structure, a way to see the invisible scaffolding shaping our galaxy. But if it's the corpse of a primordial dwarf, it could reveal what the earliest galaxies looked like before cosmic time enriched them with heavy elements. Either way, this faint stellar smear is more than debris. It's a looking glass into forces that shaped our cosmic home, written in the slow dance of stars we almost overlooked. NGC 147 should be a quiet, forgettable dwarf galaxy, a faint smudge of stars orbiting Andromeda, but zoom in and something immediately feels off. Unlike most galaxies where globular clusters, those dense balls of ancient stars, are scattered evenly. NGC 147 clutch of them huddle awkwardly on one side, like partygoers avoiding half the room. This lopsided arrangement isn't just a quirk, it's a glaring anomaly that hints at a violent past or forces we don't fully understand. Globular clusters are cosmic fossils, relics from the universe's chaotic infancy. Normally, they orbit their host galaxies in predictable spherical halos, but in NGC 147, something's clearly disturbed them. The leading theory: a close encounter with its larger neighbor, NGC 185, or perhaps even Andromeda itself. Picture two galaxies passing each other in deep space. Their gravitational tugs could have yanked NGC 147 clusters into this strange, uneven distribution. The clusters on one side might have been dragged along during the flyby, while those on the opposite side slipped free, leaving behind this cosmic imbalance. Then there's the dark matter angle. NGC 147 is old. Its stars formed over 10 billion years ago, and it's largely devoid of gas, meaning its structure shouldn't change easily. Unless, of course, its dark matter halo isn't shaped the way we expect. Most simulations assume dark matter forms smooth, symmetrical cocoons around galaxies. But if NGC 147 halo is lopsided, perhaps from an ancient collision or an uneven formation process, it could have herded the globular clusters into this odd configuration over time. Here's where things get weirder. Some of these clusters are paradoxically younger than the galaxy itself, suggesting they formed after NGC 147 prime. How? One possibility, the same gravitational encounters that displaced them also compressed pockets of leftover gas, triggering late-stage cluster formation. Or maybe they're not native to NGC 147 at all. They could be stolen goods, ripped from a smaller galaxy during a long-forgotten merger. The asymmetry isn't just a curiosity, it's a window into how galaxies evolve in crowded environments. If globular clusters can be shuffled like chess pieces by encounters or unseen dark matter, it means even the oldest structures in our universe are more dynamic than we thought. And if NGC 147 oddball arrangement is a product of its past, it forces us to ask, how many other dwarf galaxies wear similar scars, their histories written in the skewed paths of their oldest star clusters? Drifting through the constellation Aquarius like strands of cosmic seaweed, the Aquarius dwarf's tidal tails stretch across the sky, a silent testimony to the Milky Way's appetite for smaller galaxies. These wispy trails of stars aren't just debris, they're a dissection in progress, a real-time demonstration of how our galaxy consumes its neighbors. Unlike the clean, symmetrical plumes seen in textbook illustrations, these tails are tangled and asymmetric, a chaotic signature of the Milky Way's messy dining habits. What makes the Aquarius dwarf's destruction so fascinating is its slowness. While other satellite galaxies like Sagittarius were ripped apart in spectacular fashion, Aquarius is being dismantled with almost surgical precision. Its stars aren't being scattered randomly, they're being sorted. Computer simulations reveal the Milky Way's gravity acts like a cosmic sieve, funneling lighter, faster-moving stars into longer, looping tails while denser clusters resist distortion, clinging to the dwarf's core like survivors on a sinking ship. This isn't random violence, it's gravitational engineering on a galactic scale. The tails also serve as a dark matter detector. By mapping the star's motions, astronomers have found the streams bend in ways that shouldn't be possible if the Milky Way's halo were smooth and symmetrical. Instead, the distortions suggest our galaxy's dark matter is clumped filled with invisible substructures that tug and warp the tails like unseen fingers dragging through water. Some researchers even argue these kinks could be scars from past encounters with rogue dark matter halos, phantom galaxies that left no stars behind but whose gravity still lingers. But the real surprise lies in the tail's chemistry. While the Aquarius dwarf itself is metal poor typical for a small galaxy, its tidal streams contain pockets of unexpectedly rich stars, heavy with elements like iron and carbon. This shouldn't happen unless the original galaxy had hidden layers, pockets of later generation stars now being peeled away like an onion's skin. It's a clue that even the simplest dwarfs might have complex histories, their quiet exteriors masking internal dramas now being revealed only as they unravel. Comparisons to other shredded galaxies like Sagittarius highlight how no two tidal tails tell the same story. Where Sagittarius's debris forms a sprawling, multi-lobed web, Aquarius's streams are thinner, more delicate, a difference that likely reflects their original orbits and the Milky Way's evolving gravitational field. It's a reminder that galactic cannibalism isn't a one-size-fits-all process. Each digestion leaves unique fingerprints, a celestial forensics report written in starlight. As telescopes grow sharper, these tidal tails are becoming more than just casualties, they're becoming tools. By reverse engineering their paths, astronomers can trace the Aquarius dwarf's orbit backward in time, reconstructing not just its demise but the Milky Way's growth over billions of years. The tails aren't just where this galaxy ends, they're where our understanding of galactic evolution begins. and somewhere in their twisted paths, there might even be hints of the next dwarf destined to join the Milky Way's menu, a fate that, in cosmic terms, is already written in the stars. Andromeda might look like a perfectly defined spiral galaxy in photos, but peer deeper, and you'll discover its true scale, a monstrous, invisible embrace stretching 2 million light-years into the void. This is its stellar halo, a sparse, ghostly envelope of ancient stars, shredded galaxies, and dark matter that dwarfs the galaxy's visible disk by orders of magnitude. To put that in perspective, if Andromeda's spiral arms were the size of a dinner plate, its halo would be the size of a football field, a vast, uneven cloud of stellar refugees left behind by billions of years of cosmic feasting. What's truly revealing about this halo isn't just its size, but its metallicity, the traces of heavy elements like iron and carbon baked into its stars. Unlike the Milky Way's halo, which is dominated by metal-poor stars from the early universe, Andromeda's halo is a bizarre mix. Some regions glitter with metal-rich stars, as if they were forged in the cores of massive galaxies, while others remain pristine, untouched by the polluting deaths of countless supernovae. This isn't random, it's a forensic record of Andromeda's cannibal diet, a gruesome menu of galactic meals consumed over eons. The metal-rich stars are the smoking gun. They couldn't have formed in the halo's thin gas. They were stolen, ripped from smaller galaxies that once orbited Andromeda. When those galaxies were torn apart, their stars, enriched by generations of stellar explosions, were flung into the halo, creating this patchwork of cosmic leftovers. The metal-poor stars, by contrast, are likely survivors from Andromeda's own violent birth, relics of the primordial chaos that birthed it. But here's the twist: the halo's structure is far messier than simulations predicted. Instead of a smooth, spherical cloud, it's lumpy, streaked with stellar streams and clumps that betray individual acts of destruction. Some of these clumps align with known dwarf galaxies currently being digested, like Messier 32. Others are ghostly remnants of galaxies so thoroughly dismantled that only their stars remain, orbiting in silent witness to their own annihilation, the most startling revelation. Andromeda's halo might already be brushing up against the Milky Way's. At their current distances, these two gargantuan structures could be overlapping, their outermost stars mingling in a preview of the cataclysmic merger to come. It's a sobering thought. Long before the two galaxies collide head-on, their halos are already reaching out, intertwining in a dance that began billions of years ago. This halo isn't just a trophy case of Andromeda's past, it's a blueprint for its future. As it continues to cannibalize smaller galaxies, their stars will join this vast stellar graveyard, enriching it with new metals and new stories. And when the Milky Way finally meets its fate, our stars too will become part of this halo, swirling into the chaos like sugar stirred into coffee. The lesson is clear: galaxies aren't born, they're built, one violent merger at a time, and Andromeda's halo is the ultimate proof. The Cassiopeia dwarf should be a bustling hub of starlight, a compact galaxy teeming with stars packed tightly around its core. Instead, it's a cosmic paradox, a galaxy with a gaping hole at its heart. While most dwarf galaxies show a steady rise in stellar density toward their centers, Cassiopeia's core is eerily empty, a stellar void where stars seem to avoid congregating like guests steering clear of a haunted room. This isn't just a minor oddity, it's a glaring deviation from how galaxies are supposed to behave, and it's forcing astronomers to reconsider what they know about star formation, black holes, and the invisible forces shaping these cosmic islands. One explanation points to the violent legacy of a long-dead black hole. Imagine a supermassive black hole once anchoring Cassiopeia's center, feasting on gas and belching out enough energy to blast away nearby star-forming material. Over time, as the black hole exhausted its fuel and faded into dormancy, it left behind a sterile cavity where new stars couldn't ignite. This process, known as black hole feedback, is seen in massive galaxies, but Cassiopeia's small size makes it an unlikely candidate. Could a dwarf galaxy truly host a black hole powerful enough to carve such a void, or is there another mechanism at play? Then there's the delayed formation theory. Perhaps Cassiopeia's core isn't empty because stars were destroyed, but because they never formed in the first place. Simulations suggest that in some dwarf galaxies, dark matter halos can be so dense and puffy that gas gets trapped in a high-pressure stalemate, unable to cool and collapse into stars. It's like a cosmic traffic jam. The ingredients for starlight are there, but they're stuck in gridlock, suspended in a state of perpetual almost. If true, Cassiopeia's void isn't a scar, it's a fossil, preserving the exact conditions of the galaxy's stunted birth. But the plot thickens when you examine its surroundings. Cassiopeia orbits Andromeda, and some researchers argue its core might have been scoured by gravitational interactions, not with Andromeda itself, but with other dwarf galaxies. Picture a stellar game of pinball where close encounters repeatedly yanked stars from the center, leaving behind a hollowed-out shell. Supporting this idea are faint tidal streams detected around Cassiopeia, possible remnants of these chaotic encounters. The most tantalizing clue, though, lies in what isn't there. Recent surveys found no trace of the intense X-ray emissions expected from an active black hole, nor the dense star clusters typically seen in disrupted dwarfs. Instead, Cassiopeia's void is pristine, a perfect blank in the cosmic ledger. This absence is itself a revelation. Sometimes the universe's strangest secrets aren't hidden in what we see, but in what we don't. Whatever the cause, Cassiopeia's emptiness challenges the textbook view of galaxies as smooth, predictable systems. It suggests that even the smallest galaxies can harbor violent pasts, or that the rules of star formation might be more flexible than we thought. And as astronomers peer deeper into the local group's dwarfs, one question lingers. How many other galaxies are hiding similar voids, their silent cores whispering stories we're only beginning to hear? IC 5152 floats alone in the void like a cosmic castaway, an unfathomable 2.5 million light-years from the Milky Way, with no neighboring galaxies in sight. For a gas-rich, irregular galaxy, this isolation isn't just unusual, it's borderline suspicious. Most galaxies this small and brimming with hydrogen should have been absorbed by larger neighbors long ago, their gas funneled into new stars or stripped away by gravitational encounters. Yet IC 5152 lingers untouched, a pristine relic in a universe that thrives on collisions. The question isn't just how it stayed solo for billions of years, it's whether its loneliness reveals something fundamental about the local group's hidden architecture. One clue lies in its motion. Unlike most galaxies in our cosmic neighborhood, which drift toward the gravitational pull of Andromeda or the Milky Way, IC 5152 is fleeing. Precise velocity measurements show it's racing away from the local group's center, caught in the expansion of the universe itself. This puts it in a rare category, a backsplash galaxy, one flung outward after an ancient encounter with larger structures. Imagine a stone skipping across a pond. IC 5152 might have once grazed the outskirts of the local group, only to be hurled into the void by the momentum of that interaction. But here's the catch, its gas shouldn't have survived the trip. Galactic interactions, even glancing ones, typically shred fragile hydrogen clouds or trigger star formation that exhausts the supply. IC 5152 gas is not only intact but flourishing, its irregular shape studded with young blue stars. This suggests its isolation wasn't accidental. It might have been shielded, perhaps by an unusually thick dark matter halo that cushioned it during its escape. Or worse, our models of galactic interactions could be missing a crucial piece of physics, some mechanism that lets fragile galaxies slip through cosmic fingers unscathed. The broader implications are staggering. If galaxies like IC 5152 can evade mergers indefinitely, it means the local group's history is messier than we thought, not a tidy hierarchy of absorbed dwarfs, but a chaotic battlefield where some slip away unnoticed. Worse, its existence hints at a population of similar renegades lurking just beyond our surveys, their faint light drowned out by the Milky Way's glow. Every one of these outliers could rewrite the story of how galaxy clusters form and evolve, proving that even in a crowded universe, some objects play by their own rules. Perhaps the most humbling thought, IC 5152 isn't just a curiosity, it's a time machine. Its untouched gas and slow, steady star formation mirror conditions from the universe's adolescence, offering a glimpse of how galaxies behaved before cosmic crowds reshaped them. In its solitude, it holds something vanishingly rare, a memory of the cosmos before gravity drew its borders. And as telescopes probe deeper into the local group's fringes, one truth becomes clear: the universe's quietest corners often harbor its loudest revelations. The Pegasus Dwarf Irregular Galaxy might look like just another messy splatter of stars at first glance, but zoom in, and you'll discover its true drama: gaping, thousand-light-year-wide cavities blown clear through its gas clouds like cosmic Swiss cheese. These aren't just random holes, they're superbubbles, the aftermath of stellar explosions so powerful they can reshape an entire galaxy's fate. And in this unassuming dwarf, they're rewriting the playbook on how even the smallest galaxies churn their ecosystems. What's astonishing isn't just the scale of these bubbles, big enough to swallow our entire solar system 100 times over, but what created them: generations of supernova working in unison. When massive stars die, they don't go quietly. Each explosion launches a shock wave that tears through surrounding gas, pushing it outward like a snowplow. In most galaxies, these bubbles pop like soap film, their energy absorbed by denser surroundings. But Pegasus Dwarf's sparse, low-density gas lets them expand unchecked, merging into colossal voids over millions of years. The result, a galaxy pockmarked with these eerie, starless hollows, their walls glowing with the faint echo of long-dead stars. But the real magic lies in the feedback loop they've ignited. As these superbubbles grow, they do something counterintuitive: they regulate star formation. The same explosions that blast gas away also compress leftover material along the bubble's edges, triggering new rounds of stellar birth. It's a self-perpetuating cycle. Stars form, explode, carve voids, and those very voids birth the next generation of stars. Hubble images reveal young, blue star clusters lining these cavities like pearls on a string, proof that destruction and creation are two sides of the same cosmic coin. Here's where Pegasus Dwarf throws a curveball. In larger galaxies, this feedback process is tempered by gravity and turbulence, keeping star formation orderly. But in this tiny galaxy, with barely 100 million stars to its name, the feedback runs wild. Superbubbles here grow so large they sometimes break free of the galaxy entirely, venting enriched gas into intergalactic space. It's a galactic exhalation, a loss of precious star-forming material that should, in theory, leave Pegasus Dwarf a sterile wasteland. Yet somehow it persists, replenishing its gas reserves through some unseen cosmic plumbing, perhaps siphoning material from intergalactic filaments or tiny, unseen companions. The implications stretch far beyond this one oddball galaxy. If superbubbles in low-mass galaxies can eject gas this efficiently, they might explain a long-standing puzzle: why so many dwarfs in the local group are quenched, their star formation mysteriously halted. Pegasus Dwarf offers a glimpse into the mechanics of this shutdown, showing how stellar explosions can act as both midwife and executioner for galactic ecosystems. And as astronomers study its bubbles in finer detail, they're uncovering something even more profound: the delicate balance between chaos and order that governs every galaxy, from the smallest dwarfs to the grandest spirals. In the end, Pegasus Dwarf's superbubbles aren't just scars, They're signatures of the universe's relentless creative violence. The Tucana dwarf lurks in cosmic solitude, an island of stars adrift nearly 3 million light-years from the Milky Way, so isolated it makes even the void around IC 5152 look crowded. Most galaxies this far from neighbors are bustling stellar nurseries, their gas reservoirs untapped and ripe for star formation, yet Tucana defies the script. It's a cosmic fossil frozen in time, its star-making factories shuttered for nearly 10 billion years. This isn't just a galaxy that's winding down, it's one that slammed on the brakes in the universe's infancy and never restarted, leaving astronomers scrambling to explain why. The mystery starts with its gas. Unlike typical quenched dwarfs, which have been stripped bare by encounters with larger galaxies, Tucana remains suspiciously plump with hydrogen. Ordinarily, this gas should be collapsing into new stars, but here it just lingers like an unopened fuel canister beside a cold engine. The galaxy's color tells the story. Its stars glow uniformly red, the telltale sign of a system where stellar birth ceased so long ago that even the shortest-lived stars have faded into old age. It's as if someone flipped a switch, cutting off star formation while leaving the gas untouched. So what could have caused such a sudden shutdown? One theory points to internal rebellion. In the early universe, dwarf galaxies like Tucana might have experienced hyperactive star formation, their first generations of stars burning out in explosive supernova that blasted away remaining gas before it could cool and collapse anew. But Tucana's gas didn't escape, it's still there, just stubbornly inert. Unless those ancient supernovae heated the gas to temperatures where it couldn't condense, creating a self-imposed star-forming blockade that persists to this day. Then there's the dark matter twist. Simulations suggest some isolated dwarfs could have dark matter halos so diffuse they struggle to hold onto their gas, letting it puff outward like steam from a kettle until it's too thin to form stars. Yet Tucana's gravity appears strong enough to keep its gas anchored, ruling out this explanation. Unless, of course, its dark matter isn't distributed as we assume, perhaps clumped in ways that create dead zones where gas can't pool densely enough to ignite new stars. The most tantalizing clue might lie in something we can't see, ultraviolet radiation from the early universe. During the cosmic dawn, when the first galaxies ignited, their fierce UV light could have penetrated even isolated dwarfs like Tucana, ionizing their gas and preventing it from cooling. But if that's the case, why did other field dwarfs like Leo T escape this fate? The answer might hinge on timing. Tucana could have formed in a rare pocket where this radiation persisted longer, or where its gas was particularly vulnerable to heating. Comparisons to other local group dwarfs only deepen the puzzle. Take Pegasus dwarf, another gas-rich irregular, where stellar feedback carves superbubbles but can't fully quench star formation. Or consider Andromeda Roman 19, a ghostly giant where star formation never really began. Tucana fits neither mold. It's a galaxy that did form stars even prolifically before hitting an invisible wall. The implications ripple across cosmology. If isolated galaxies can self-quench without external interference, it means our models of galactic evolution are missing a critical piece of physics, some mechanism that can slam the door on star formation without removing the fuel. It also raises a haunting question. How many other Tucanas are hiding in the voids between galaxy clusters, their stories of arrested development written in light we've yet to capture? For now, this cosmic hermit keeps its secrets close, a relic of an era when the rules of star formation might have been written in bolder, stranger strokes. Its very existence whispers that even in the emptiest corners of the universe, galaxies don't always play by the rules, and sometimes the most revealing outliers are the ones that refuse to act their age. Scientists have long been captivated by Andromeda's double nucleus, a galactic oddity that refuses to fit neatly into any textbook explanation. but recent advancements in supercomputer simulations and cutting-edge telescope technology are peeling back the layers of this cosmic mystery, revealing possibilities even more bizarre than we imagined. One leading theory suggests the secondary nucleus isn't just debris from an ancient collision. It could be the remnant of a third supermassive black hole, one that failed to merge with Andromeda's central behemoth and now orbits it in a gravitational standoff. This scenario isn't as far-fetched as it sounds. When galaxies collide, their central black holes eventually spiral together, but the process can take billions of years. In the chaotic interim, multiple black holes might circle each other like prize-fighters in a ring, their gravitational kicks flinging stars into lopsided configurations. State-of-the-art simulations from the University of Colorado show that under the right conditions, a smaller black hole could carve out a stable orbit just a few light-years from the primary, shepherding stars into the faint secondary clump we observe today. The catch: such a black hole would be nearly invisible, hidden in the glare of surrounding stars unless, of course, it's actively feeding. That's where the James Webb Space Telescope enters the picture. Upcoming JWST observations aim to dissect the infrared light from Andromeda's core with unprecedented precision, hunting for the telltale heat signature of accreting material around a potential third black hole. Even more tantalizing are plans to track individual stars in the secondary nucleus over time. If their motions reveal an unseen gravitational anchor, it would be the smoking gun for this theory and a rare chance to study a multi-black hole system up close. But not all researchers are convinced. A competing school of thought argues the secondary nucleus might be an illusion, a dense, elliptical disk of stars orbiting the primary black hole at an angle, creating the appearance of a second core when viewed from Earth. Advanced models from the Harvard-Smithsonian Center for Astrophysics show how such a disk, tilted relative to Andromeda's main plane, could reflect light in ways that mimic a separate structure. The key test: measuring stellar velocities in 3 dimensions. If stars in the secondary nucleus follow the same orbital plane as those around the primary, the disk theory gains credence. Early results from the Keck Observatory's adaptive optics system hint at this very alignment, though the data remains hotly contested. What makes this debate so pivotal is its implications for galactic evolution. If Andromeda's double nucleus stems from an unresolved merger, it suggests even mature galaxies can harbor unfinished business, black holes locked in cosmic détente for eons. If it's a trick of perspective, it forces us to reconsider how we interpret similar structures in distant galaxies. Either way, the answer will reshape our understanding of how galactic cores form, collide, and ultimately unify. The most exciting possibility: neither theory may be entirely correct. New work from the European Space Agency posits that the secondary nucleus could be a transient phenomenon, a stellar swarm temporarily amplified by gravitational lensing from dark matter clumps near Andromeda's center. This would make the double nucleus a fleeting cosmic mirage, one that might vanish or shift over astronomical timescales. Upcoming gravitational wave detectors like LISA could settle the matter by probing the space-time ripples from Andromeda's core, searching for the distinctive hum of orbiting black holes. As JWST and next-generation telescopes turn their gaze toward Andromeda, one thing is certain: this galactic enigma isn't just a curiosity, it's a live experiment in extreme physics. Whether it reveals hidden black holes, warped stellar disks, or something entirely unexpected, the double nucleus promises to remind us that even our closest galactic neighbor still guards profound secrets. And in solving them, we might just unlock the playbook for how all galaxies, including our own, transform over cosmic time. The Pegasus dwarf galaxy shouldn't be this heavy. On paper, it's a wispy, unremarkable smudge of stars, barely a tenth the size of the Milky Way, yet measurements of its gravitational pull tell a different story entirely. Stars on its outskirts orbit far faster than the visible mass can explain, as if the galaxy is anchored by some invisible hand. This discrepancy lies at the heart of one of cosmology's fiercest debates. Is Pegasus dwarf drowning in dark matter, or is gravity itself playing by different rules here? The conventional answer points to cold dark matter, the unseen scaffolding thought to bind the universe. Models suggest Pegasus dwarf, like most small galaxies, should be swaddled in a dense halo of this mysterious substance, accounting for its extra gravity. But there's a hitch. Its dark matter seems too concentrated, packed into a smaller volume than simulations predict. Some researchers argue this could hint at interactions between dark matter particles we haven't accounted for, a tweak to the standard model that would make halos clumpier in dwarfs. Others propose Pegasus might have formed inside a rare, ultra-dense knot of dark matter in the early universe, a cosmic anomaly frozen in time. Then there's the radical alternative, MUND, or modified Newtonian dynamics. This controversial framework suggests dark matter doesn't exist at all. Instead, gravity strengthens where conventional physics says it should weaken, like in the faint outskirts of galaxies. Pegasus dwarf is a textbook MUND candidate. Its rotation curve, the way stars speed up at its edges, matches MUND predictions eerily well without needing invisible particles. Supporters point out that similar discrepancies plague other dwarfs, like Triangulum and Andromeda Roman 19, as if the universe is nudging us toward rewriting gravity itself. But MUND faces its own hurdles. For one, Pegasus dwarf's gas distribution shows subtle irregularities that better align with dark matter models. Then there's the broader cosmic web. Dark matter elegantly explains galaxy clusters and the universe's large-scale structure, while MUND requires additional tweaks to fit. Some theorists now explore hybrid theories. What if dark matter exists but interacts differently in low-density environments like dwarfs, mimicking MUND effects? The stakes here extend far beyond one galaxy. If Pegasus dwarf's gravity defies conventional models, it could mean our understanding of cosmic structure is fundamentally flawed, or that dark matter is far stranger than we imagined. Upcoming telescopes like the Vera Rubin Observatory may settle the debate by mapping the motions of individual stars in Pegasus with unprecedented precision. Until then, this unassuming dwarf remains a battleground for competing visions of the universe, proving that sometimes the deepest mysteries hide in the smallest packages. From rogue black holes to starless gas clouds, cosmic fossils to cannibalized dwarfs, the local group's strangest objects don't just defy expectations, they rewrite the rules. These 30 enigmas prove our cosmic backyard is anything but ordinary. Each one cracks open a new question. How can a galaxy thrive without dark matter? Why do some black holes feed star formation instead of stifling it? What carved perfect rings into the heart of Hoag's object? The answers aren't just curiosities, they're clues to the universe's deepest workings, hidden in plain sight less than a few million light-years away. These oddities force us to rethink the basics. Galactic evolution isn't a tidy, one-size-fits-all process. It's a messy, improvisational dance where mergers, gravity, and sheer cosmic luck collide. The Phoenix cluster shouldn't be birthing stars, yet it does. Leo the First shouldn't orbit backward, yet here it is. Andromeda's double nucleus, the Magellanic Stream's starless river, Tucana dwarf's inexplicable hibernation. Each one exposes gaps in our models, reminding us how much we still don't know. But that's the thrill of it. Every mystery solved unveils 10 more, and the local group is our closest laboratory. These aren't distant specks in some far-off supercluster. They're our neighbors, close enough to study in stunning detail. Their quirks aren't just academic, they're previews of our Milky Way's fate when it collides with Andromeda, or blueprints for how galaxies might evolve in the universe's loneliest voids. Now it's your turn. Which of these cosmic rebels fascinates you the most? Is it the phantom black holes of IC10, the primordial purity of Sextans A, Or the sheer audacity of Hercules' dwarf stretching itself thin against the Milky Way's pull? Drop your pick in the comments. We'll dive deeper into the top choices in future videos. And if you're hungry for more galactic oddities, hit subscribe. The universe has endless enigmas waiting, and we're just getting